you.
Hold on, let me just disconnect audio.
Okay. Yep. Okay. Can you guys hear me? Yeah, yeah. So today we're gonna go over midterm two review session, and I see that some people sent me a list of what they wanted to go over. So the list I have is is let's see here. Let me look at this one. The meaning of superimposable and chirality, switching RNS in IUPAC nomenclature, optical activity, like dextrorotatory, levorotatory, like racemic mixture, 50-50 each, enantiomeric excess, Fischer projections, enantiomers, diastereomers, meso compounds, chiral resolving agent, ENZ designation, chair confirmations, and also drawing chemical form structures, right? With multiple choice problems. So I think the best way to do this is to go over Fahrenheit's practice problems because the exam is gonna be like very similar to that, right? So is it on chapter 6 and 7? The upcoming midterm on when is it? Is it on Monday?
Monday on
Mhm.
chapters 5, 6, and 7.
5, 6, and 7. Okay, okay. Um, so let's see here. How do you guys feel about chapters 5, 6, and 7 so far? Like what chapter is the most confusing for you guys so far? Mhm. See here. Okay. See. Okay. See. Okay. I think what we could do is OE2 reaction, chapter 7. Okay, yeah, like chapters SN1, SN2, E1, E2. Oh yeah, E2 with the anti-paraplanar. Yeah. So we'll go over that as well. Um okay, yeah, with those reactions. See here. So let me just give a brief overview of those reactions. Okay. So let's talk about SN2 reaction first. Have you guys learned about that yet? SN2. Let's start with that.
Yeah.
Okay. So SN2, some observations are gonna be like this right here, where we're going to have an electrophile with a good leaving group, right? Reacting with some nucleophile. Let's make this general. And then we know that this carbon here is going to be partial positive because the leaving group here is going to tend to be an electronegative atom, like bromine or chlorine, making that carbon partial positive, the electrophile, which this nucleophile here is going to attack that electrophilic carbon, kick out the good leaving group, and substitute that leaving group with the nucleophile, whatever that nucleophile is. And the mechanism here is going to be a backside attack, meaning that the stereochemistry would invert, right? So an example of that would be something like this, where let's say we have this secondary haloalkane reacting with NaCN and a protosolvent solvent DMSO, right? The a protosolvent solvent DMSO will not do anything in the reaction. It's just going to be there to facilitate the reaction. Well, oops, let's see here. Okay. See. Okay. So whenever you see Na, right, that's gonna be positively charged. Whenever you see Cn, like whatever's attached to the Na is gonna be negatively charged, right? So that means that the nucleophile here is gonna be the Cn minus. The electrophile here is gonna be this carbon right here, that's partial positive, and this right here is gonna be the good leaving group. Okay. And this Cn minus here is going to attack this electrophilic carbon, do a backside attack. And then what's that doing is that this Cn here is trying to make a bond with that electrophilic carbon right there. And that's a problem if we don't do anything else because we know that this carbon here already has 4 bonds, right? 1, 2, 3, 4. But when this CN here is trying to make a new bond with that carbon right there, that's gonna have 5 bonds. So to conserve the octet rule, right? We're gonna kick out one group, and the best group to leave here is this bromine here, because when this bromine leaves with the 2 electrons right there, those 2 electrons are stabilized, right? Because this bromine here is very electronegative. But because that's happening, like through a backside attack mechanism, the new bond is going to be the opposite of whatever bond the leaving group was. So in this case, because the leaving group bond was a wedge, we're going to invert the wedge into a dash, right? The CN here is approaching this carbon here on the backside or the dash, creating a bond right there. And then this bond right here in the wedge is getting kicked off to the bromine right there, giving a Br minus ion side product like that. Okay? So this doesn't always mean that it's gonna invert from R to S or S to R, right? Because when you give R or S to this chiral center here, what would that be? Would this chiral center be R or S?
It would be S.
It would be S. Okay, so let's see here. This is gonna be 1, this is 2, this is 3, and then we rotate this way, which is counterclockwise, and that is S. And we don't have to invert anything here because the hydrogen going back is a dash already, and that's the most important part for assigning RNS. Make sure the lowest priority group is on the backside, the dash, right? So that's an S right there. How about this chiral center over here? Would this be an R or an S?
It would be R.
It would be R, right? So this would be 1, this is 2, this is 3. So this is going to be counterclockwise as well, which looks like S because it's going counterclockwise. But if you look at the lowest priority group, which is this hydrogen over here, it's at the front, the wedge, right? So the shortcut to do this is just to do it regularly and then invert whatever the result is. So because it looks like S, it's actually going to be R, right? That would only work if the lowest priority group is a wedge. You could use that trick if the lowest priority group is a wedge. If the lowest priority group was a let's say a flat planar bond like that, that trick would not always work. You would actually have to do rotation there, right? But we notice here that the stereochemistry inverted from S to R. That's not always the case because let's say, for example, we have something like this. Let's do this right here. Let's say we have that. See, let's do actually let's do this right here. Okay. Okay, and let's do NaCN DMSO. Okay, so we see here this carbon here is a substrate because it's attached to the good leaving group, chlorine. And this substrate here specifically is bonded to like 2 other carbons, so we'll call that a secondary substrate, right? Because it's bonded to 2 other carbons. And we see here the nucleophile here is the Cn minus ion, cyanide ion, which is going to attack this carbon through a backside attack, kick out that leaving group, and then invert the stereochemistry from a dash to a wedge like this. Okay? Okay. Now, what would be the configuration of this chiral center over here on the reactant side? R or S?
R.
R. Okay, so let's see here. This is going to be 1. This is 2. This is 3. So going this way is counterclockwise, which looks S. But the lowest priority group here is on the wedge. So we're going to invert that to an R. So that is an R right there. Nice. Okay. Now, what about this one right here?
S.
S. Yeah, so let's see here. This is going to be 1, 2, 3. Okay, so this one here is a little bit tricky.
It remains R still.
It remains R because if I draw out this carbon here that is triple bonded to this nitrile, this carbon and this carbon is tied in terms of atomic number. Then we look at what's attached to these carbons that is not the chiral center. This carbon here is attached to the nitrogen 3 times. This carbon here is attached to the oxygen 3 times, right? 1, 2, 3. Now, what has a higher atomic number, oxygen or nitrogen?
Oxygen.
Oxygen, right? Will have a higher atomic number, which will make this have the number 1 priority, this one number 2. This one number 3. And if you go this way, that's clockwise, which is R, and it stays R because the lowest priority group a is on the back, the dash, right? So we see here that even though the bond changes like from a dash to a wedge, the stereochemistry stays the same. Like the RS configuration stays the same. It stays R, right? Um, so that's why whenever you do SN2 backside attack inversion, the bond will always invert. Like wedge will always invert to dash, or dash will always invert to wedge. But that doesn't always mean that R will invert to S or S will invert to R, right? In most cases, it will like this. But some exceptions, like this reaction here, this Carl center here stays as R, right? Okay.
Brian, I have a
Yeah.
question.
Mm-hmm.
Can you clarify what the DMSO is at the bottom? Like,
Mm-hmm.
what does that do?
Yeah. So the DMSO at the bottom right here is an aprotic solvent, right? So before I explain what an aprotic solvent is, let me explain what a protic solvent is, because that protic solvent there is going to be important for SN1 E1 reactions. Okay, so protic is going to mean that that solvent there is going to have hydrogen bonds, H bonds, right? Meaning that the hydrogens are going to be attached to one of these 3 atoms, FON, fluorine, oxygen, or nitrogen, right? So some examples of protic solvents are going to be water, H2O, alcohol, ROH, where R is a hydrocarbon chain. It could be anything. It could be an ethyl group, isopropyl group, terbutyl group, um, right? Or it could be, let's say, carboxylic acid, right? Because we see that there is a hydrogen here attached to one of those 3 atoms, fluorine, oxygen, or nitrogen. It could be a primary amine. It could be ammonia. It could be secondary amine, right? But it cannot be a tertiary amine, right? It cannot be a tertiary amine, right? Because this tertiary amine here has no hydrogen bonds, right? This is a nitrogen atom here, which is one of the 3 atoms, fluorine, oxygen, or nitrogen, but there's no hydrogens attached to that nitrogen right there. So because of that, there's no hydrogen bond, right? The hydrogen bonds are very important. Like they're one of the strongest intermolecular bonds because of the difference in polarity, like the difference in electronegativity, right? So if we look at water here, for example, this oxygen here is so electronegative compared to the hydrogen that it's going to be partial negative, making the hydrogens partial positive, right? So the hydrogen bonds, the H's would be partial positively charged, right? Okay. A protic solvent is going to be like no H bonds, right? No H bonds. So I don't actually know what the structure of DMSO looks like, but if I look it up, there won't be an H bond. So let me search up what a DMSO structure is. See, so DMSO would be dimethyl sulfoxide, which is going to be 2 methyl groups attached to a sulfur that is double bonded to an oxygen, right? We see that oxygen here is one of those 3 atoms, but there's no hydrogens attached to the oxygen, so there's no H bond there. There are hydrogens here, but these hydrogens here are attached to carbon, right? Which is not one of those 3 atoms, 3 atoms, fluorine, oxygen, or nitrogen, so there won't be any H bonds, right? Carbon is not electronegative enough to make hydrogen like partial positive charge, right? And this right here, because it's a product, it won't interfere with the reaction, right? Like this Cn minus here, it won't be surrounded by partial positive hydrogens, right? Like if it was water or alcohol, the partial positive hydrogens would surround the nucleophile, making the nucleophile weaker. But because this is a proto solvent, it's just gonna be like there to facilitate the reaction, to make the ions exist somewhere. Like the Na ion is gonna float around DMSO solvent, and the Cn minus is gonna float around DMSO solvent, but that solvent itself is not gonna react. This is a spectated ion, the Na sodium ion, so that won't react. The reacting species here is this nucleophile, Cn minus cyanide ion, right? So SN2 would work in a protic solvent that won't react with the reaction. Okay. Does that make sense, Ashna?
Yes, it does. Thank
Uh-huh.
you.
Yep, of course, of course. Okay. Now, another important factor about SN2 reaction is that it's gonna prefer less steric hindrance, because we notice here that when we do the reaction, when the nucleophile approaches the electrophile in the backside, it needs space to do that, right? This is a secondary substrate here, meaning that it's attached to 2 other carbons. If we try to do SN2 with a tertiary carbon, that won't happen because it's too much steric hindrance, right? So let's say we have something like this with bromine, and if we do NiCN, DMSO, there won't be SN2 reaction, no SN2 reaction, right? Because this carbon here is a tertiary carbon since it's attached to three other carbons, one, two, three. That means that it's very bulky, so much space around it, so crowded, steric hindrance, right? The Cn minus here that we have and the reagent cannot reach that electrophile, cannot do a backside attack. It's too crowded. Okay. Okay. SN2 would work best with methyl electrophiles, right, or substrates. Then primary, and then secondary would be moderate, right? Tertiary would be no reaction, it's too bulky, too crowded. Okay. Methyl meaning that we have a CH3Br. Primary meaning that we have the electrophile bonded to one other carbon. Secondary meaning that we have the substrate carbon being attached to two other carbons. Okay. Any questions on that concept for SN2 reaction and steric hindrance? Okay, so now that's SN2 right there. Another important thing is about the reagent, right? Because when you're determining what reaction it is, given the substrate, reagent, and solvent, it's kind of difficult to choose between what reaction you're doing, like SN2, SN1, E1, or E2 reaction, right? And here are the four things that I look at. The first thing I look at is the substrate, right? Rather, like whether it is methyl substrate, if it is primary unhindered substrate, primary hindered substrate, uh, a secondary substrate or a tertiary substrate, right? And that would be a very important piece of information to determine what kind of reaction we're going to do, SN2, SN1, E1, or E2. The other thing I look at is the type of reagent, right? More specifically, the type of base and nucleophile the reagent is. And there's four different types of it. There's going to be a weak base, strong nucleophile. It could be strong base, strong nucleophile that is small. It could be a strong base, strong nucleophile that is bulky, or it could be a weak base, weak nucleophile, right? And I'm really gonna tell you here, and we're gonna do examples of it. The weak base, strong nucleophiles will tend to do SN2 reactions. Strong base, strong nucleophiles, the small ones are gonna be like, are gonna do E2 reactions, and the bulky ones, right? But the small one is gonna do Zaitsev E2. Whereas the bulky, small base, strong base, I mean bulky, strong base, strong nucleophile is gonna do Hoffman E2. Okay, and I'll go over what that means. When I go over E2 examples, and then the weak base, weak nucleophile are gonna do SN1, E1. Whenever an SN1 reaction happens, an E1 reaction will also happen, right? But the major product would be SN1, right? Unless heat is added. If heat is added, then it's gonna favor the E1 reaction. Okay. So we went over SN2 already with the weak base strong nucleophile, and I'll give examples of some of them. There's Cn minus, there's N3 minus, there's the halogens, Cl minus, Br minus, I minus. There's the neutral amines. It has to be neutral amines. It can be negatively charged. If it's negatively charged, it would be something else. There's the phosphorus, right, with the pair of electrons. So those like are the SN2 reagents that you'll most likely see. Okay. Now, do you guys want to go over SN1 E1 reactions next or E2 reactions next?
SN1.
E2.
SN1 E1. Okay. Okay. Let's do SN1 E1 and then let's do E2 after.
Brian, I have a
Yeah.
question regarding the reagents. So,
Mm-hmm.
like, one thing I get really confused by is sometimes when it's like an alcohol, like methanol, ethanol, it does like SN1E1,
Mm-hmm.
but then
Yeah.
I notice sometimes when the alcohol is paired, is it when it's paired with the salt, it does E2?
Oh, right. So you're thinking about this, like NaOCH2, CH3, and then the solvent is gonna be neutral version of that, which is CH2CH2OH, right?
Yeah,
Like
so
this version, right? Yeah.
yeah, like
So,
every time I see like a carbon chain with an alcohol, I get really confused. I'm like, is it a strong alcohol or is it like a weak alcohol?
yeah. So, a very important thing to know is about the salt, like you said, like Na or K, right? They're gonna be the same thing because whenever you see that, what charge is that associated with?
Positive?
Positive charge, meaning that whatever is attached to it has to be negatively charged, right? But this Na here is a spectral ion that won't do anything in the reaction. The thing that's negatively charged is this ethoxide ion here. And when you see an oxygen with a negative charge like that, that is attached to an R group, that alkoxide ion is going to be a strong base, strong nucleophile, right? And then when you have a strong base, strong nucleophile, it's going to do an E2 reaction, right? This right here, the product solvent won't do anything in the E2 reaction. It's just there to have these ethoxide ions swim around somewhere. Like it can't just exist there like out of nowhere. It has to exist there, swim in somewhere, and it's gonna swim in the neutral version of it, which is the solvent right here. This is a product solvent.
Okay. That
Uh-huh.
makes
Right. But if you had like just this alone, then that right there would tend to do SN1E1 reaction if it's just that neutral molecule alone.
okay.
Yeah. Mm-hmm. Right. Joseph had your hand up.
Yeah, I just had a quick question. So
Uh-huh.
like, let's say you had, so I know like if you had a tert butyl with a bromine on it, it would be considered what do you call it, hindered? What if you had a
Mm-hmm.
isopropyl bromine? Would that be considered hindered?
Isopropyl, bro, like this right here?
Yeah.
Yeah.
Or sorry, wait, add an
Uh-huh.
extra chain like to the
Uh-huh.
isopropyl, like an extra
Oh,
carbon.
actual carbon like this or right
No, no,
here.
no. So it's like a isopropyl, then
Uh-huh.
another carbon, then bromine.
Another carbon isopropyl. Oh, I see. Okay. Like this.
Yeah, yeah.
Okay. Yeah. So this right here, that's a good question, right? Because this is gotta get trying to get like into like the primary substrates because this carbon here is the substrate since it's directly attached to the good leaving group. And this is a primary substrate because it's attached to one other carbon, but the carbon that it's attached to, right, is branched. It has more than one uh, uh, group attached to it, right? So that's what we call a primary hindered substrate. Whereas if you had this substrate here, where this is also a primary substrate attached to the good leaving group, that primary substrate there is unhindered, right? And it's unhindered, right? They're both primary, right? Because they're both attached to one carbon. But the difference here is that the carbon that they're attached to can be hindered or unhindered. If it has more than one group like this one on the left does, it's a primary hindered substrate. If it only has one or less groups, then it's gonna be unhindered, right? And then that's gonna be important for SN1E1 reaction. Like this difference here is important for SN1E1 type reactions, which we're gonna go over next. But does that make sense, Joseph? Like any other questions on that?
No, yeah, that makes sense. Thank you.
Yeah. Okay. So first, okay. Okay. Um, and so now let's go over SN1E1 type reactions. They always go together. And the important thing about this is that, well, let me just show you here. Let's say we have this haloalkane right here, which is a secondary substrate, and we react it with um weak base, weak nucleophile. And there's only three of them that I want you guys to know. Two of them are the most common for SN1E1. It's gonna be water and alcohol. Those are the common ones that you're seeing, right? You could also see carboxylic acid as well. But notice how these reagents here are neutral, right? There's no charge associated with it. There's no negative charge, there's no positive charge, right? Now this alcohol here, it could vary with what the R group is, but let's just use ethanol, for example. Now, is this a product or a product solvent here? Ethanol.
Product.
Product solvent,
Okay.
right? Because we have an H bond. We have this bond here, which is between an oxygen and hydrogen, which means that we have a partial positive hydrogen and a partial negative oxygen on the product solvent. Um, we know the bromine is partial negative, right? And the substrate is partial positive. or the electrophile is partial positive. Now, if we put this and this together, we have a lot of alcohols around where the partial positive hydrogens are gonna surround the leaving group. They're gonna they're gonna do solvolysis here, right? All these hydrogens here that I'm drawing are alcohol hydrogens, right? I'm not drawing out the other ones, but these hydrogens here are partial positive of the alcohol right there. They're gonna wrap around the bromine and carry it away, right? And then just kick out the leaving group. The leaving group would just leave as the first step for SN1E1 reactions. Okay. When that happens right there, this carbon here loses a bond, and because it loses a bond, what charge would this carbon have?
Positive.
Positive charge, right? And when you see a carbon with a positive charge, we call that a carbocation. Okay? And there is carbocation stability. Like if I give you these carbocations over here, the carbocation stability would increase from left to right, right? And that's because of something called hyperconjugation. Okay, so that's basically saying that this carbon here with the positive charge is stable with more groups around it. And think of it like this as an analogy, like this carbon here is missing a bond, so the more friends or groups it has around it, the more stable it's gonna be. This carbon here is the least stable because it has no R groups, right? So it's not gonna donate electrons. But this one here, because it has R groups, they're gonna inductively donate electrons to the carbocation, making it more stable, making it more neutral, right? The secondary one here has two friends, two R groups donating electrons to it. This primary carbocation only has one friend, one R group donating electrons to it. This methyl carbocation here has no friends, right? No R groups donating electrons to it, so it's the least stable. Okay. Okay, so to keep this carbocation stability in mind. So here we see that we have a secondary carbocation because this carbon here is attached to two other carbons. Okay. Now for SN1 reaction, we're gonna bring in the alcohol, and the alcohol is gonna act as a nucleophile, right? Which is gonna have this oxygen here attack this carbocation and form a new bond between that carbon and oxygen right here, which is going to be this intermediate right here, right? This right here is the new bond that we formed. New bond, right? And if I highlight it in a different color, like if I highlight it as yellow, that new bond right there in yellow came from that pair of electrons right here in yellow, right? Because a bond represents two electrons. These two electrons here came from that pair of electrons on oxygen, meaning that this oxygen here only has one pair of electrons left, which is this one right here that didn't react. And if you calculate formal charge, right? I feel like from Gen Chem, like we know oxygen is on the sixth column or sixth group of the periodic table, so it wants 6 electrons to itself. So 6 minus 1, 2, 3, 4, 5. Oxygen has 5 electrons to itself. 6 minus 5 is plus 1, so oxygen here has a positive charge right there. Okay. Now we can neutralize this. We can make it more stable, right? Because oxygen here with this positive charge is very angry, very unstable right now. It doesn't like that positive charge, right? But to neutralize it and make it more stable, we can deprotonate it, right? And to do that, we're gonna use another alcohol, right? Because we have a lot of this around. But this time, this alcohol here is gonna act as a base and grab that hydrogen right there. And then this bond between the hydrogen and oxygen, those two electrons are gonna go into the oxygen right there, right? And then that's gonna stabilize and neutralize the the oxygen right there. Okay. And this is the SN1 product right here. So to summarize, yeah. Any questions on this one?
Can't the why can't the bromine come in and
Oh,
activate
yeah.
it?
So it could be the alcohol or the bromine. You could use the bromine as well in the mechanism. But there are a lot more alcohols in the solution compared to one bromine that left. So more realistically, more likely, the alcohol is gonna deprotonate that. But on the test, if you draw a bromine minus ion grabbing that would also work as well. So that could also work.
Okay, and then I have another question. So
Yeah.
when that alcohol comes in and takes that hydrogen,
Mm-hmm.
wouldn't that alcohol that took the hydrogen become a get a positive charge itself?
Mm-hmm. Yeah, right. And that's gonna be the side product right there, like that, because this oxygen here gained a bond to hydrogen, right? we're using, let's say, if I highlight this pair of electrons in purple right there, that purple pair of electrons right there is going to be this new bond right here, right? That grabbed, let's say, this pink hydrogen, which is going to be this pink hydrogen right here, right? And then if you calculate the formal charge of this oxygen, 6 minus 1, 2, 3, 4, 5, 5 is positive 1. So this would be positively charged, which is the side product, the side product. If you used Br minus to grab the hydrogen instead, to deprotonate this positively charged oxygen, you would get HBr as a side product, right? Which could also be your answer, right? Um, so that's a side product right there, which professors don't usually ask about. They usually ask about the main major product, which is the SN1 product right here, right? But that's a good question for the full mechanism. Okay. Now that's SN1. We said earlier that SN1 and E1 reactions always go together, right? Let's use the same reactant and reagent. The intermediate is the same. We'll always form a carbocation intermediate for both SN1 and E1. So if you see this reactant and reagent right here, what is the very first step of the mechanism?
Leaving group leaves.
Leaving group leaves to form the carbocation intermediate, which is this right here. And I didn't give you guys this example yet, but whenever you form a carbocation intermediate, you always have to stop because a lot of students forget about this next step here. Sometimes there's a carbocation rearrangement step, right? It could be a hydride shift or a methyl shift to make the carbocation more stable. And we talked about the carbocation stability, like methyl carbocation, primary carbocation, secondary carbocation, tertiary carbocation. The more substituted the carbocation is, the more stable it's going to be, right? In this case, we have a secondary carbocation, so we have to stop and say like to the right and left of it, if it can become more stable. To the right is a primary position, so we don't want that. So we don't want to move the carbocation there. To the left, it's a secondary position, but it's already secondary, so we don't have to like move that there because that's extra energy that the molecule doesn't have to do, right? So in this case, we don't have to do any carbocation rearrangements. Okay. Now from there, in SN1, we used another alcohol to attack it right away, but now for E1, right? We're gonna form a double bond, an alkene, in elimination reactions. Okay. So this carbon here, that is the carbocation carbon is the first carbon, right? That's the alpha carbon right there. The second carbon away from the alpha carbon is the beta carbon. Okay. Um, Now for elimination reactions, we're gonna do an acid-base reaction. Those beta carbons have to have at least one beta hydrogen, one beta proton, right? So I'm just gonna drop one beta proton right here, and we're gonna form double bonds right here. Um, are you guys familiar with double bond stability? Like, let's say if I give you this list right here. Are you guys familiar with which double bond is the most stable, and which double bond is the least stable? And these are for E1, E2 reactions here.
The tetra substituted
Yep,
double bond is the most stable.
yep. This is the most stable, the tetra substituted one. This is the unsubstituted one, so that's the least stable. So stability here will increase from left to right, right? So this is gonna be stability. And to tell like what it is, like just look at the carbons of the alkene and see how many groups are coming off of the alkene, right? We see like these carbons here are the carbons of the alkene. We see four groups coming out. One, two, three, four, right? So we see that this is a
Wait, is this the
tetra
fancy yarn you bought online?
substituted one, right? And then we see that this right here is a tri-substituted one. These three here are di-substituted. This is mono-substituted, and this is unsubstituted, right? Now this one here, geminal alkene, is going to be similar stability as cis alkene, right? And this is a trans alkene, okay? Now, the reason why transalkene is more stable than cis and geminal alkene is because of steric hindrance, right? If you look at these two groups right here, they're facing away from each other as far as possible. They're not gonna bump into each other. Whereas the cis and geminal alkenes, like the two groups are so close to each other that they're gonna have steric hindrance for both the cis and geminal alkene. Okay. Okay, so for E1 reaction, if we want to make the more stable alkene, do we want to go for hydrogen A or hydrogen B? If we want to make the more stable alkene from this intermediate.
A.
A, right? Because the next step for E1 is to grab that more substituted beta proton. The bond between the more substituted beta proton and beta carbon right there is going to go to make a double bond right there between the alpha and beta carbon to give us this disubstituted alkene here, which is our major E1 product. Our major E1 product. Okay. That's not the only E1 product that we can get though, right? Because we see that we could also grab hydrogen B, which if we did, we would get this alkene right here. We grab that proton, the bond between that proton and carbon will go there to make that double bond. So that's the other E1 product. And we have one more E1 product here, right? And this other one can be a little bit tricky to see because can this bond here rotate like that?
Yes.
Yep, it can. So if that bond rotates like that and I redraw it here before we do the acid-base reaction, we could still grab that same proton, right? But if we grab it from this position and create a double bond here, we would create this double bond right here, which is still disubstituted like the major E1 product, but it's a different type of disubstituted E1 product, right? The major one is trans, whereas this one here is cis. Right, so we have three E1 products here. This trans alkene, this cis alkene, and this mono substituted alkene right there. Yeah. Okay. Yes, Ashna?
I had a question regarding hydride shifts.
Yeah.
Shifts. Can you like explain when we have to do when do we prioritize a hydride shift and when do we prioritize a methyl shift?
Yeah. So hydride shift versus methyl shift. We would always want to do a hydride shift first before methyl shift. If we cannot do a methyl shift, I mean a hydride shift, if we cannot do a hydride shift, then we would do an alkyl shift, like a methyl shift. So for example, let's do one with a hydride shift first. If we have something like this, and I'm gonna have you guys describe to me the SL1 and E1 products here for this one. Okay. Okay. Oh, another important thing about SN1, which might be a conceptual question, is that what is the hybridization of this carbon right here? That's the carbocation. Is it sp hybridized, sp2 hybridized, or sp3 hybridized?
SP2.
sp2, right? Which is going to be flat and planar. So when the nucleophile comes into attack, it could attack on the top side or bottom side, giving a wedge or a dash, right? So it's 50-50. And in this case, it's the racemic mixture, right? Racemic meaning that there's going to be 50% of one enantiomer, 50% of another enantiomer, right? Okay. Now, let's say we have this molecule over here and we react it with isopropanol. What do you guys think of when you guys see this reactant and reagent here?
It has to be either SN1 or E1.
Yep, because we have a secondary substrate, which is good to form a carbocation, right? It's not a methyl substrate. It's not a primary substrate. If it was a methyl or a primary substrate, then it would not work, right? Unless it's a primary hindered substrate, which we'll go over that as well after. We have a protic solvent, which is a weak base, weak nucleophile. The first step is to kick out the good leaving group to form a carbocation intermediate. Like that. Okay. Once we have this carbocation intermediate, what do we have to stop and look out for?
hydride shift?
Hydride shift, right? So if we look to the right of it, that's primary. We don't want to go there. Look to the left of it, that's tertiary. We do want to go there because that's more stable than secondary. And in this case, we see if this carbon here has a hydrogen, and it does. So I'm gonna draw that bond out with the hydrogen to shift that hydrogen there with the bond, to get this new intermediate right here. Right? This carbon here gained a bond with the hydrogen that I shifted over. This carbon here lost the bond with the hydrogen, and because it lost the bond, it's positively charged now. Now we have our more stable carbocation intermediate. Now let's say we're doing SN1 mechanism. What is the next step for SN1 mechanism?
The nucleophile comes in.
The nucleophile, in this case, the alcohol, isopropanol, will come in to attack that electrophilic carbon and create a bond right there, which is going to give us this new bond right here. This is the new bond I drew out between that carbon that got attacked by that oxygen, which is attached to an isopropyl group, a hydrogen, and it has one pair of electrons left, giving it a positive charge. Now, what can we do to neutralize this positively charged oxygen? What can we do to make it more stable?
Take out the hydrogen.
Deprotonate it.
Yep, deprotonate it, take out the hydrogen, and you could use one or two things here. You could use the leaving group that left, Cl minus, right? Or you could use alcohol. Now let's use Cl minus. If we use Cl minus to grab that hydrogen, the bond here between the hydrogen being grabbed and oxygen is going to go to that oxygen, giving it a pair of electrons and making it stable, giving us this SN1 product here, this ether here, like that. Okay, and side product HCl. Okay. Okay, yeah. When you click the Cl minus is floating around, so, and then it floats around, and then we could use that Cl minus to do the last step here, right? Or we could use another equivalent of the alcohol to do the same. Okay. Okay. So now let's talk about this right here. Okay. Oh, this is a good leaving group right here. What is the first step that you guys think is going to happen here in this mechanism?
Leaving
If-
group leaves.
Leaving group leaves to form what kind of intermediate? Right. This carbon here would be positively charged, which is a carbocation intermediate. And from here, if you look to the right of it, that's primary. We don't want to form that because that's less stable. If we look to the left of it, it's more substituted. So we do want to go there because it has more hyperconjugation, but there's no hydrogens there, right? There's three methyl groups, right? 1, 2, 3. So we could use one of the methyl groups here to shift that methyl group over to that carbon right there, which is going to give us this new intermediate right here, right? Where the red methyl that I circled is that red methyl group right there. Because this carbon here lost the bond to a methyl group, that carbon right there is going to be positively charged like that, right? The positive charge is no longer here because it gained a bond to a methyl group like that. Okay. Now, if we do the SN1 mechanism, the nucleophile will come in this case it's water, to attack the electrophile. And then that's the new bond right there to oxygen that's bonded to two hydrogens, positive charge, deprotonate it using the leaving group, OTS, or another water molecule to act as a base, and deprotonate it to our neutral product right here. Okay, so that's SN1. Methyl shift, right? Let's do E1 with this right here. So the E1 mechanism would be the same up until we get the most stable carbocation intermediate after the methyl shift. What will you guys do now? If you more E1 from this here. What is the next step?
Find the one with the most substitution for your alkene.
Yeah, for the most stable, most substituted alkene, and that's gonna come off the beta carbons. And these right here are gonna be the beta carbons, right? And we're interested in one of the beta protons. So I'm drawing out all the beta protons here. And let's say A, B, and C, those are the beta protons that we're interested in. Which one is the most substituted beta proton?
B.
B is the most substituted beta proton because it's coming off of a carbon that is tertiary, right? So we're gonna use the base here, which we could use water or the leaving group, to grab that more substituted beta proton. The bond here between the beta proton being grabbed and beta carbon is gonna go and make a double bond right here between the alpha and beta carbon, which is gonna form our tetra substituted alkene, right? Because these carbons here are the carbons of the alkene. There's four groups coming out of it. One, two there, three, four there. Okay, that's the most stable E1 product right there. Okay, any questions on this hydride and methyl shift mechanism?
Wait, I have a question about just SN1 reactions. When does it always result in a racemic mixture, or when does it, like, how do you tell when it does?
Yeah, so it won't always result in a racemic mixture, right? Because let's say we have this reacting molecule here, and I'm going to do this quickly here because we went over this mechanism already, but I'm going to describe it in terms of like racemic or not. So let's say we have this reagent, which is protic. We're going to do SN1E1 here. The first step, kick out the leaving group to form the carbocation intermediate. Stop, see if you can do any hydride methyl shift. It's already at its most stable position, so we don't have to worry about that. Now, when water comes here to attack, right, it could attack on the top or bottom side because this carbon here is sp2 hybridized, making it flat and planar. So water can either attack on the top, giving us a wedge intermediate like this, right? Or it could attack on the back, giving us a dashed intermediate like this, right? And then let's just finish off the mechanism here on one of them, which I'm going to use this top one right here, deprotonate it, make it neutral, give us this neutral product here with SN1. This right here is one of the products because we know the other product can be dashed alcohol. And I'm going to put this symbol right here, plus minus, or you could say plus enantiomer, right? Because we know the other product is going to be that dashed bond right there, which could be 50-50, right? We could get 50% of that or 50% of the other one. And that is going to be a racemic mixture, right? Racemic mixture, right? Because we know that this is the only chiral center in the molecule. And if that only chiral center in the molecule can change in the other product, like from a wedge to a dash, 50% and 50% on the other one, that's a racemic mixture. An example where you cannot say racemic mixture is when, let's say, we have something like this. Right? And we try to do, let's say, SN1 again. First step, kick out the leaving group, form the carbocation intermediate, and then have the nucleophile attack. Right? We stop and see if there's any hydride methyl shift. This one is not gonna make it better, so there's no hydride methyl shifts here. Right? Now we could say like it attacks on the top side, giving a wedge. It could be a dash as well, but let's say it's a wedge, leading to that intermediate, and then we use a base like that or the leaving group to deprotonate and neutralize that positive charge oxygen to give us this final product right here, which we cannot say a racemic mixture. We cannot use this symbol right here, right? Because if we say that symbol right there, that means that both chiral centers would flip because we're talking about enantiomers here, right? But the only chiral center that would flip is the one that reacts, which is the one with the ether. So our two products here are going to be that product on the top and this product right here, right? And these right here are not enantiomers of each other, right? They're diastereomers of each other because some chiral centers stay the same, some chiral centers change. We see that this chiral center here that pre-existed stays the same. Nothing touches that chiral center in the reaction at all. It stays the same, right? But the reacting center changes, right? Which is the one that changes. So that's diastereomers. And if they're diastereomers, we can't call that a racemic mixture. right? So
Okay, thank you. Yeah.
yep, yep. So if there's another chiral center in the molecule, you can't say racemic mixture. If there's only one chiral center in the molecule, then you can say racemic mixture, right? Just in short. Okay. Okay, so now let's talk about concerted shifts. Like when we talk about primary unhindered and primary hindered substrates before, let's say we have something like this and something like this. What would you guys what do you guys think is gonna happen here? What's gonna is there gonna be anything, or is there gonna be like no reaction?
It's
No
gonna be no
reaction.
reaction.
No reaction, right? Because if you guys try to do SN1 reaction and kick out the leaving group first, we're gonna get this carbocation right here, which is a primary carbocation, and that's too unstable to exist. So that would be no reaction right there. Right? We said the stable carbocations are able to exist are secondary or tertiary carbocations. Okay? But this carbon right here is primary. And is it primary hindered or primary unhindered? Like
Unhindered.
unhindered, right? Because the thing that it's attached to is bonded to something that is not branched, right? It only has one group attached to it. So that's primary unhindered. Okay. Now, if we have something like this, for example, and we use the same reagent, ethanol, right? Now, this one here is a little bit tricky because this one here is a primary substrate as well. So if you try to kick off that good leaving group bromine, you would get a primary carbocation, which is unstable to exist, and that's true. It cannot exist like that, right? But we notice here that this is a primary hindered substrate because the thing that's attached to this primary carbon here is branched. It has more than one group attached to it, right? So what we're gonna do here is a concerted shift, right? Concerted hydride shift specifically, right? Concerted hydride shift, meaning that before, like we're gonna do a hydride shift and kick out the leaving group at the same time. Before we would just kick out the leaving group first without the hydride shift, but we're gonna do the hydride shift and kick out the leaving group at the same time. So hydride shift there, kick out the leaving group to form a tertiary carbocation like that. In the previous example, we couldn't do that because it isn't hindered. We need a primary hindered substrate to do that, right? To make it stable enough. Like you can say that we could do a hydride shift here and kick it out to form a secondary carbocation. But that wasn't observed in experiments, right? In experiments, they see that this concerted hydride shift happens with primary hindered substrate instead of primary unhindered substrates. Okay? Okay. And then we just continue on with this normal mechanism. Nucleophile attacks the electrophile. And then deprotonate to make it neutral. Okay. Okay.
Wait, so
So that's yep.
it's gonna happen like there's gonna be a hydride shift, not a methyl shift here, right?
Yep. Yep. There's gonna be a concerted hydride shift here, not a concerted methyl shift. There can be a concerted methyl shift here because let's say, for example, there wasn't a hydrogen here, but instead that was a methyl group. So instead of moving the hydrogen, you could move the entire methyl group over there. So like your new product would be would be would be like that instead. If that was a methyl group and you did a wait. What? Not like this. So yeah, it would be like that if you did a methyl shift instead. If you did a considered methyl group instead. Right.
Okay, thank you.
Yep. But this right here is a concerted hydride shift, right? Okay. Let me just give you yeah.
Sorry, wouldn't this just not even have a reaction to begin with?
So this one here, it looks like there's no reaction to begin with, but there is actually going to be a reaction because of the concerted hydride shift, because of this primary hindered substrate. Fahrenheit might not have gone over this reaction. Do you guys remember seeing something like this, concerted hydride shift or concerted methyl shift in lecture?
No,
No,
he's not
he-
gone over hydride or
Okay,
methyl
okay.
shift.
Okay, so we don't have to worry about that here. We don't have to worry about that here in this class. Okay. Right. That's good. Okay. You guys ready to move on to E2? E2 reactions with the anti-periplane transition state? Okay, let's do
Yes.
that. Let's do that. Mhm. E2. So this is the scariest one compared to SN1, E1, and SN2 because there's so many different examples of it with the anti-periplanet transition state. But let's start off simple, right? Let's start off with a secondary haloalkane right here, and they're gonna work with strong bases and strong nucleophiles, right? Like NaOH and water, let's say for example. And like we said earlier, E reactions will always form double bonds, alkenes, right? And we already talked about the alkene stability. The more substituted the alkene is, the more stable it's going to be, right? And they're going to work with the beta protons. This is an alpha carbon right here because it's going to be the first carbon attached to the good leaving group, bromine right here, right? These right here are going to be the beta carbons because they're the second carbon away from the good leaving group. And we're only interested in one of the beta protons, like either HA or HB. And we see here that HA is more substituted. So that's the proton that we're interested in. So this base right here, the strong base, is gonna grab that more substituted beta proton, where this bond right here between the proton being grabbed and carbon is gonna go over there to create a double bond, and then kick out this good leaving group at the same time. These three arrows here happen simultaneously, happen in a concerted step, right? As the base here grabs the more substituted beta proton, this bond here between the beta proton and beta carbon goes to make a double bond here between the alpha and beta carbon, kicking out this good leaving group, right? We have to kick that out because if we don't kick that out, that's going to break the octet row. Like, if we try to kick a double bond right here, this carbon will have 5 bonds, right? And that's not good. Like, that breaks the octet row. To conserve the octet row, kick out the good leaving group right there, which will lead to this product right here and the resulting H2O molecule after we use this base hydroxide ion to get protonated, right? So that's the most simple example I could think of for E2. Any questions on that before I move on to the next example? Okay, so if you grabbed the less substituted beta proton instead and create a double bond here, kick out the leaving group, you would end up with this alkene, which is not as stable, right? Because this is a mono substituted alkene, whereas the alkene here is a di substituted alkene, so that's more stable. Okay? Okay. So now moving on to the next one. Let's talk about anti-periplanar transition state now. So if I give you, let's say, something like this right here, and I give you a strong base, strong nucleophile like NaOCH2CH3, right? We know that we want to get the most substituted beta proton. If this is the alpha carbon, this is the beta carbon, this is the beta carbon, right here. We know that we're beta carbon that we're interested in is this one right here because it's more substituted, which will lead to the more substituted alkene. But we see the hydrogen right here coming off of that beta carbon is a wedge, right? Wedge, say you say that this is your product right here, right? The isopropyl here is like it wasn't, but it's fine because this carbon is sp2 hybridized now. This right here would be incorrect because it doesn't follow the anti-periplanar transition state rule, right? Does not follow anti transition. What the anti-periplanar transition state is saying that the beta proton being grabbed in E2 reaction has to be anti to the good leaving group. It has to be opposite to the good leaving group. So in this case, here, the good living group is a wedge. We want on here to be a dash for the mechanism, right? But right now it's a wedge, so that's why if we do it as is, we're gonna get the wrong product. But what we can do is that we can rotate it in a way that would make the hydrogen a dash, right? So the way that I like to do it is I know this right here, this bond between the alpha and beta carbon, I'm interested in. Do free rotation. So I could this single bond right there, and I'm gonna keep everything on this side the same, right? Let me switch my Wi-Fi. I think I'm lagging a little bit. Okay. Hello, hello. Can you guys hear me?
Yeah, we can hear you.
Okay, that's good. So I'm gonna keep this side the same, and I'm gonna rotate these three groups right here. That hydrogen, this isopropyl, and this methyl group right there. Okay. Now I want the hydrogen to be a dash, so I'm gonna move the hydrogen in a a clockwise direction, right? And to move the hydrogen to where this isopropyl group is, which will force this isopropyl group to be a flat bond, which will force the methyl group to become a wedge bond, like that. This is gonna stay stationary. It stays still. And then as a result, I'm gonna redraw that like this. We said that this stays stationary. Every other bond will stay the same. So that's a flat bond. This is a wedge. This is a dash. The wedge is now a methyl. The dash is now a hydrogen. The flat bond is now an isopropyl group. Any questions on how I did that rotation right there? Like this structure here is the same exact structure as this structure over here, right? And we could confirm that by like assigning R and S for this car center. This car center here is gonna be, let's say, this is 1, this is 2, this is 3. It looks R, but it's actually S because the lowest priority group is in the front. So this is also S, right? Because we know that this is going to be 1, this is 2, this is 3. And going this way is counterclockwise, which is going to be S, and it stays S because the lowest priority group is a hydrogen right there, right? Any questions on like the technique though, on how we redrew it to this, where the hydrogen is on the backside now, the dash, like when we're rotating these three groups here, keeping this group the same?
Is there like a rule that you can apply, like only switch two groups?
So you cannot just switch two groups. Like if let's say you keep this methyl group the same, right? And you keep like everything here the same, and you just switch these two, right? Like let's say you made the hydrogen a dash, and then you made the isopropyl a wedge, right? That wouldn't be the same molecule, right? That would be diastereomer molecule, right? If you rotate groups, you have to move three groups around in orbit. Right? Because imagine you had a model kit and then you held this part of the model in the model kit like with your one hand, and then you twisted this bond right here around, which would twist or orbit these three groups around. Like they're gonna go in circles like that. Right? And then when they go in circles, like this is just a point in time where the three groups can be in, like that.
Okay, yeah, that
Yeah.
makes sense.
Yep. And now we see that this beta proton here is anti or opposite to that good living group, which is good, right? That follows the anti-periplanar transition state. So that's going to lead to the right product, which if we grab that, make a double bond here, kick out the good living group, we're going to form this alkene right there, which is tri-substituted, which is different than this alkene right there, right? Because we see that if we make a line through the double bond right here, the isopropyl group is on the same side as the methyl group on the other side on that incorrect structure, but on the correct structure, the isopropyl group is on the opposite side as the opposite methyl, like that, right? This one here does not follow the anti-periplanar transition state. That's incorrect. This one here does follow the anti-periplanar transition state, so that is correct right here. Okay. A shortcut, if you were looking for a shortcut without doing this rotation stuff right here, is I would say do it normally, right? And then once you do it normally, just flip these two around to get to the right structure like that. That's a shortcut that you could use to get the right product. Any questions on this? Okay.
We
Let
do
me get
another
uh-huh.
example.
Yeah,
Oh.
let's do more examples. Yep, let's do that. Okay. Okay. What's your thought process when you see this right here?
That it's E2.
E2, right? Because the substrate that we see here is secondary. The reagent that we see here is that when you see K, it's positive. This is negative, and the thing that's negative here is OR minus, strong base, strong nucleophile. Oh yeah, which is gonna be small, right? I'll go over the bulky ones with the Hoffman example after this, but if it's small, it's gonna be able to form the Morse substituted alkene. It's gonna be able to form the Zaitsev alkene, right? And we see that this is the alpha carbon. These are the beta carbons, and we're gonna be interested in the beta protons, right? But if we want to make the more substituted alkene, more stable alkene, we're gonna look at this beta carbon here because it's more substituted, right? Now this hydrogen here is a dash. What would happen next here to predict the product, to draw out the mechanism to get the product?
We would have to flip it.
Mm-hmm. We have to rotate it to make this beta proton here anti to this good leaving group, right? So what bond are you going to rotate specifically?
The bond like in between the hydrogen and the chlorine.
Like this bond right here.
Yeah.
Yep, between the alpha carbon and beta carbon, right? We're gonna rotate those groups right there. I'm gonna keep everything here the same, and then I'm gonna rotate this ethyl group, this cyclopentyl group, and this hydrogen around. What direction are we gonna rotate it to? In one one step, you could rotate in either direction and get the same thing. But if I want to do it in one step, one turn, do I want to rotate it clockwise or counterclockwise?
Clockwise?
Clockwise, right? Because we want the hydrogen to be a wedge, which, wait, wait, let's see here. Oh, so in this case, it's gonna be counterclockwise. You can do clockwise, but you have to do it 2 times. But if I only want to do it 1 time, I'm gonna rotate it counterclockwise. Oh, wait, yeah, counterclockwise, yeah, counterclockwise, right? Because I want the hydrogen to be where the wedge is, which is right here. And to get to that in one step, I'm gonna rotate it counterclockwise, which will force the cyclopentyl group to be where the flat bond is, which will force this ethyl group to be where this dash group is right there. Does that make sense on why I rotated it counterclockwise like that? Right? Because the goal here is to make this hydrogen a wedge. And the reason why I want to make it a wedge is because it's anti to this good leaving group. It's opposite to the dash right there. Right? So when I do that, I'm going to get this right here where the hydrogen is a wedge. The cyclopentyl group is now a flat bond. And then the ethyl group is now a dash like that. This structure is the exact same structure as the structure over here. Right? Okay. Okay. Let's see. Yeah. So once we have that, where the hydrogen is on the anti side as a leaving group, the strong base here is gonna come in, grab that proton, make a double bond right there between the alpha and beta carbon, kick out the leaving group, and lead us to our E2 product right here. And then this dashed ethyl group right here becomes a flat ethyl group because it's attached to an sp2 carbon now. We can't have wedges or dashes on flat sp2 carbons like that, right? That was the long way to do it, but if you want to do it the short way, the shortcut way, let me erase all these so that doesn't get in the way. Okay, let's just do it normally. Get that hydrogen, make a double bond right there, kick out the good leaving group, and what you'll get initially is going to be incorrect, which is this, right? But to get the right answer, just flip this and this around, which will get you here, right? And that's the correct answer, which follows the anti-peri planar transition state, meaning that the beta proton you grab is going to be anti to the good leaving group right there. Right, this one here leads to the wrong answer because this hydrogen here is not anti to this good leaving group. It's not on the opposite side as that leaving group right there. Okay, any questions on that? Do you guys want to try another example?
Wait, is it fine if can I ask you to work on a certain
Mhm.
molecule?
Yeah. You could send a screenshot of the
Or
problem here on Zoom, and then we could work through that problem. Or is it on one of Farhad's practice problems here?
No, it's not. Can I just tell you the name? I know the name of the molecule.
Yeah.
It's 2-bromo, 2-methyl heptane.
Heptane. So 2, 3, 4, 5, 6, 7. 1, 2,
And then
3, 4, 5, 6, 7. 2-bromo, 2-methyl.
yep.
Okay.
And then you're gonna have for your nucleophile, you're gonna have um tert butyl oxide potassium.
Okay.
And then for your solvent, you're gonna have a polyprotic tert butyl alcohol. Yeah,
Yep.
there we go.
Oh yeah. So this goes on to Hoffman E2 right here. Right. We see that this is gonna be the strong base, strong nucleophile that we're interested in because whenever we see K, that's positive charge, ignore that. Whatever is attached to us, negative charge, that's the strong base, strong nucleophile where we have a negative charge on the oxygen attached to our group. But this strong base, strong nucleophile here is bulky. Right? It's so crowded. This turbidal here is very crowded. So much steric hindrance there. So we see that this is the good leaving group. This is the alpha carbon, the first carbon attached to it. And these are the beta carbons right here. In the previous examples, we said that in order to get the more substituted alkene, more stable alkene, we want the most substituted beta carbon, which is this one right here, right? So it would want to grab that hydrogen right there, but it cannot because it's so crowded. It's too sterically hindered, right? So it's forced to go to one of the less substituted beta proton to form the less substituted beta alkene, which is going to be that right there, right? Which is a disubstitute alkene. It would want to grab this beta proton here to create double bond and kick out the leaving group to get this double bond, the more stable one, but it cannot because it's a bulky base, right? Too much steric hindrance.
Oh, sorry.
Uh-huh.
Why can't it do the other beta, like the left beta? Because wouldn't that also be two substituted thingies?
Yep. So it could do this one as well. If you grab this one right here, make a double bond right here, kick out the leaving group, that's gonna form this double bond right here. And they're gonna be the same because if you rotate the single bond right here, this double bond and single bond are gonna orbit into each other's places. So they're the same molecule, same product.
Oh shoot, yeah, you're right.
Yeah.
Okay.
It's okay. It's okay. Yeah. Okay. Um, that's good. Okay. So that's Hoffman right there when you use a bulky base. And the two bulky bases that I want you guys to know for 118 series is the turbutoxide, right? Which you could see as what you saw there, the one I drew on bond line form, or you could see it in condensed formula like this, or you could see it written out in letters like this, right? And instead of K, you can see it as Na. It's gonna be the same thing for turbutoxide, or you can see LDA in letters like that, which is lithium diisopropylamine, right? Lithium diisopropylamine, which will look like this. Lithium is positive charge. The amine here will have a negative charge with two isopropyl groups here. And this right here is a strong base, and it's bulky because of these two isopropyl groups right there. It's sterically hindered, right? Okay. Work on the mechanism on the for remain on the last question. This one, okay. This one, let me see. Okay. So when I open that up, let me give you guys one tricky example here. If I have this right here, and let's say we have this and react it with NaOH and water, what do you guys think the product is going to be here from this reactant and reagent?
E2.
E2, right? Because we have a secondary substrate, good leaving group, strong base, hydroxide ion. Now, we know this is the alpha carbon, this is the beta carbon. And then from there, what can we do to predict the E2 product here? Right? What proton are we interested in? Which proton are we interested in to grab?
The one with the tert butyl.
So this one right here. Right? Because it's more substituted. That's what we've been saying in the previous examples, right? But the hydrogen here on the more substituted beta carbon is a wedge, right? And they're not anti to each other, right? Because they're both wedges, they're not opposite to each other. And in the previous cases, we could fix that problem by rotating it. But can this single bond here rotate?
No.
No, right? Because it's part of a ring. So we cannot get that at all. It's impossible, right? So we would have to get this proton here that is anti, like to this leaving group, make a double bond there, kick that out, and we would get this double bond right here, where the trip will stay as a dash, like that.
Wait, this might be kind of a silly question, but how did you know that the hydrogen on the other one had to be anti?
Yeah, so for E2, right, it would always have to be anti-periplanar transition state, but this one here on the other side, there's two hydrogens, right? And because we already see two bonds that are flat and planar, there's missing like a dash and wedge bond, and we see two hydrogens on that carbon, which one is a wedge, one is a dash. But I'm grabbing the dash one because that is the one that would follow the anti-periplanar transition state. The other hydrogen that is a wedge would not follow the anti-periplanar transition state, so I'm not gonna use that one. But it was invisible, so I didn't draw that one out because that wouldn't follow the mechanism correctly.
What if there was like a double bond on that? Like between the bromine and then the carbon that we were grabbing, then would there be no reaction?
Oh, like if there was a double bond right here between this carbon and this carbon right here.
Yeah.
Yeah. So let's see here. Hydrogen. So let me write that out. Let's see here. So this bromine here would no longer be wedge, it would be flat. And I said this is the hydrogen right here. Yeah, you can still do it, but let's see here. NaOH, H2O, OH minus here would grab this proton, make an extra pi bond there, kick that bromine out, and that's gonna create a triple bond in the ring right here, which is very unstable because what is the bond angle of sp hybridized carbon? What is the preferred bond angle?
180.
180 degree. This triple bond here is forced to become inside a ring, which is less than 180 because it's kind of bent like that. So this is very unstable. But in 118C, you'll learn that this will happen in some of the reactions. But this will exist in a very short amount of time in the mechanism. Okay? This is possible, but we won't worry about that now.
Wait, I have a question. So,
Yeah. Mm-hmm.
what if like stereochemistry just wasn't given? Like, how do you know if it's antiplanar at that point? Would you have to do
Yeah.
Newman's or something?
No. If they're not given at all, like no wedge, no dash, then you assume like that's easier. You don't have to worry about it, the anti-periplanar at all. If you're given a
Uh,
wedge or dash, then that's harder because they're gonna test if you know anti-periplanar or not. But if they don't give you a wedge or dash, you don't have to worry about it. You just assume.
so I just take whatever hydrogen I want. And then just
Hmm.
say it's anti-paraplanar.
Yeah. Yeah. If there's no wedge or dash is given. Yeah.
Wow. Okay.
Yeah. Which Fahrenheit might give on his problems. Yeah. hmm Okay, this one.
Would there ever be a case where you would have to use Newman's? Like, that's what I'm worried about. Like, trying to find
Mm.
the anti-paraplanar using Newman's or a conformation ring.
Oh, confirmation ring. Yes, like yeah, that is good because let's say we have something like this, and then we have something like this. Let's say this is the good leaving group here, and then we use a base like this, where if this is the good leaving group, this is the alpha carbon, these are the beta carbons, but I'm gonna be interested in this one because, or actually no, they're both equally substituted. Let's just say because they're both equally substituted, um, it doesn't matter which one you grab. Let's say I'm gonna focus on this one. Which hydrogen would you grab? The axial or equatorial hydrogen?
Axial.
Axial, right? Because the axial hydrogen here is facing straight down, which is gonna be anti to this bromine facing straight up, like that. Okay, so if you draw the mechanism here, you're gonna grab this hydrogen here specifically to create a double bond between this alpha and beta carbon and kick out that leaving group bromine right there, which will form that double bond right here, like that. Newman projections, we can still follow the anti-periplanar transition state because let's say that's the leaving group right there. And then let's say these are hydrogens, right? Let's say this is hydrogen A, this is B, this is C. Which hydrogen would you grab to follow the anti-periplanar transition state?
A.
Yep, A, because that's anti to the leaving group. So the OH minus here will grab this most substituted hydrogen, and then it's gonna create a double bond, like right there between this dot and this back carbon, which we do not see. Right? It's invisible, like it's hiding behind that red dot carbon, and then kick out the leaving group, like that, right? Because in the wind projections, it's like this is your eye right here, some eyelashes, and then let's say you look down straight at this carbon right here. That's gonna be the red dot carbon, and then this is the blue carbon in the back. You do not see this bond right here between the red and blue carbon right there. It's hiding behind the red carbon, right? Which that's where the double bond is gonna be formed in that mechanism. Okay. Okay. Um. Yeah. Mhm. Okay. Kobayashi would also work for cyclohexane, but how do we learn it in 118CA out of curiosity? Kobayashi. I've never seen that before. Let me see what that Kobayashi thing is. Kobayashi. Organic chemistry. Okay. Let's see. I'm not sure what that is, but you can send me a screenshot of what Kobayashi is, and then I'll take a look closer at it. Okay. Okay. Now let me go over some practice exams that Ashna sent me and the mechanism of that. Let's say we have this reactive molecule here. Okay. And we react it with multiple different reagents. Okay. 1, 2, 4. This is the one I gave her. Okay. 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 And we went over every one of these reactions already. Let's focus on the first one. What do you guys think is gonna happen in the first reaction, which is this one right here with the first reagent?
The azide is going to substitute through SN2.
Yep. Azide is going to substitute through SN2, so the mechanism will look like this. N3 minus, backside attack the electrophile, kick out the good leaving group, invert the dash into a wedge, giving us this product right here. Okay, second one. What do you guys think is going to happen in the second reaction here?
SN1.
SN1 or E1, right? And the mechanism here, I'm gonna actually draw out because there's gonna be something kind of tricky that a lot of students forget about. What's the very first step of SN1, E1?
The leaving group leaves.
Yep, leaving it leaves, forming a carbocation. What's the next step after we form the carbocation intermediate?
You look for a shift.
Yeah, look for a shift. That's the part where a lot of students forget about. In this case, we could do a hydride shift on the left side, moving that whole hydrogen with the bond over to that carbocation to form a more stable tertiary carbocation, like that. And then let's say from here, we could either diverge into SN1 mechanism or E1 mechanism. Let's say we do SN1 first. For SN1, the nucleophile here, methanol, would attack that carbocation. And then we would have this intermediate, right? Where because it's flat and planar, we can have wedge or dash, doesn't matter. And it's OCH3H positive. And then we could deprotonate it with Br minus or another base to make it neutral to get our SN1 product. Okay, OCH3. And in this case, there's no other pre-existing Carr center. It's only this Carr center that is changing. So we can say that this is a racemic mixture, right? If there was like another pre-existing Carr center like that, we cannot say it's racemic. We would have to actually draw it out where this flips, right? Keeping the same pre-existing Carr center that is unreacted with. Okay, that's the SN1 product right there. For E1, let's start with the more substituted carbocation here. What are you looking for E1 mechanism here?
Of substitution.
Yep, the most substituted beta proton. So this is the carbocation. This is the alpha carbon. These are the beta carbons. This beta carbon here is the most substituted beta carbon, but there's no hydrogens there to grab from. There's no protons on that beta carbon because this beta carbon here already has 4 bonds. 1, 2, 3, 4. So the next most substituted beta carbon with at least 1 beta proton is this one right here. So we're gonna use the base to grab that proton and form a double bond right there, which is going to give us this alkene right there, which is the major E1 product. Here's going to be the minor ones, right? If you grab this beta proton instead, you would form this double bond. Oh wait, yeah. We can actually rotate this. So this is actually not the major one because if we flip that bond, rotate that bond, we could get a trans. Oh no, actually this is trans. Okay, this is E alkene. So this is actually the major one. But another product that you could get is this right here. right, which is a Z alkene. Right? And you could get that by rotating the single bond before doing the acid-base reaction to get this Z alkene. Right? This is an E alkene because the more like the highest priority group on this carbon here is opposite to the lowest priority group on this carbon here. Right, the highest priority group of that carbon right there, right? E. And then Z is when the two groups here are on the same side for Z, right? Okay. And this right here is geminal. Yeah, geminal alkene. Okay. Okay.
I had a question. How did you know that the cis was the major? Because isn't like
Mm-hmm.
trans more stable? So then should it like
Mm-hmm.
trans be the major?
Yeah, so this one here, I also thought this was major because I thought this was trans, but I just realized that we can only say trans and cis if the alkene has exactly two substituents, right? This alkene here has three substituents, so we can't say cis or trans. We have to move to E or Z configuration, right? You can only say cis or trans if it has exactly two. So if this wasn't here, then you could say like this is trans and this is cis. But because that's there with like three substituents, we could not say cis or trans anymore. So then we got to see like which one has less steric hindrance. This one here has less steric hindrance because the bulky group, which is the benzyl group here, um, is opposite to this methyl group over here. Whereas in this structure here, the benzyl group is like sterically hindered with that methyl group right there.
Okay, thank you.
Yeah. Yeah. hmm Yeah. Okay. So now let's move on to the next one, which is going to be this one here. What reaction is this going to happen? Is going to happen between this reagent and this reactant over here?
E2.
E2. Yes, E2. Um, Now, like you said, there's no wedge or dash given here, so you could just assume that it's gonna be anti, right? This is the alpha carbon. This is the more substituted beta carbon. The base here, the strong base, is gonna grab that more substituted beta carbon, high hydrogen, make a double bond there, kick out the leaving group, and give us this major E2 product right here, which is Zaitsev, the more substituted one. How about this last reagent here?
E2.
E2 as well, but Hoffman, right? It wants to also get the more substituted beta proton, but it cannot because it's too big, right? Too bulky, too crowded, too sterically hindered. So it could get the less substituted one where there's more space available for it to grab, make a double bond there, and kick it out, which will form the less substituted alkene, the Hoffman alkene, like that.
I have a quick question.
Yeah.
I know you say you can assume. What about if, like, let's say in this case, the bromine was on the same plane, and then you were given stereochem for your hydrogens? Would that change anything, or is that also an
Mhm.
assumption?
Yeah, that would also be an assumption. That would
Okay.
also be an assumption. Yeah.
All right. Thank you.
Yeah, of course. Okay. Now, if this was a wedge right here, then that would make it more difficult, right? Because let's see, let's actually do that because I don't know if that will show up on the exam or not. And let's do it just in case it does. What would you guys do if that was a wedge right there?
You rotate it.
Mm-hmm. You would rotate this single bond here between the alpha and beta carbon. So I'm going to draw out the hydrogen here, that is a dash, which is not anti to the good leaving group here. To make it anti, we gotta rotate it. Wait, I'm gonna rotate these three groups here in the counterclockwise fashion in this structure, which is gonna give us this new structure here. And then we got this. Okay, now we see the beta proton is anti to the good leaving group, where the strong base can now grab, make a double bond, kick out the leaving group, leading to our correct E2 Zaitsev product. Wait, this is not hydrogen. This is a methyl group. Okay. Product. Benzyl. Like that. Okay. Okay. Do we need to know Hoffman, Zaitsev? We didn't learn that in class. Oh, did you guys learn about it in class? Zaitsev, Hoffman with the bulky base, and small base? Like, did you guys learn about turbotoxide and LDA yet?
He didn't. I'm pretty sure he taught us the bulky ones, but he didn't teach us Hoffman and Zaitsev.
Oh,
Yeah,
okay.
he just
Like
said LDA KTBUO can
Mhm.
only do primary alkenes. That's the extent of what he said.
Oh, he said it could only do primary positions like this right here. Let's see. Okay.
Yeah,
Mm,
Yeah, I was gonna say he went over those as they were saying, but he never used like the names that you were
mhm.
saying, the Zaitsev and
And
yeah.
Hoffman. Okay, okay. Yeah, that's interesting. Yeah. Hmm. Yeah, those names are just names to classify the reaction. But the important thing is like understanding the concept behind it. The reason why he said that it only works with the primary so like position is because there's more space for the bulky base to reach that primary hydrogen right there. Like more space for that to happen, which is Hoffman, right? That's good. That's good. Okay. Okay. Um, okay, that's one set that I created. The other set I created was this right here. How do you guys feel about NMR IR? Or you guys learning that yet? NMR IR stuff or no?
It won't be on the mid.
Oh, it's not gonna be in the midterm?
It will be on the final
Oh,
though.
it will be in the final. Okay, okay. That's good. Yeah. SN1, E1, SN2, E2 is the last topic you guys learned before the midterm this coming Monday?
Think so.
Okay, okay, that's good. Okay. Uh, okay. First reaction with this reactant.
SN2?
SN2, right? SH minus attack carbon, kick out the leaving group, substitute the chlorine with the nucleophile. In this case, like there's no stereochemistry, so we don't have to worry about inversion, like inverting the wedge to dash or dash to wedge. Just put SH right there. It's good. And this is very preferable for SN2 because it's a primary substrate. There's more space, right? If this was a tertiary substrate, it won't do SN2. Next one.
No reaction.
E1.
So SN1, E1, it looks like it. Oh yeah, huh. And Farhat
Wait,
didn't go over concerted as well, because I was gonna say
he
like
he didn't,
uh
so it would be no reaction, right?
no reaction. Yeah, it would be no reaction for Farhat because this is a primary substrate, and if you kick it out, you're gonna form a primary carbocation, which is too unstable to exist. Right, so that would lead to no reaction. If there was another group there, like a methyl group, and you kick it out to form a carbocation, that would be a reaction because that carbocation is stable to exist right there. Okay. Okay. Next one.
E2?
E2. And in this case, the hydrogen here is a dash. The leaving group is not a dash or wedge, so we just assume that's anti. Where the base here is going to grab that proton, create a double bond there, kick out the leaving group to form this double bond right here. Like that. Okay. LDA is also the same, but it has no choice. There's only one beta carbon with one beta proton. There's no like other beta proton to grab, so it's gonna lead to the same product as the last one. Right. Like that. Okay. Um, can we go over the math that would be on the midterm, like optical purity and anything else calculation based? Yeah. So that one I didn't learn when I took the class, like with enantiomeric excess and optical activity, but is anyone here familiar with how to do that? Do that?
Yeah, I am.
Oh yeah, okay. Do you have an iPad or tablet?
Let me pull something up real quick.
Okay. Yeah, that's good. That's good. Because like I need to learn that as well. I didn't learn because I had Nasiri for when it's in A. Oh no, wait, no, I had leave-ins. I had leave-ins for once in A, and then Nasiri for when it's in B and C. Yeah, so I didn't learn about that
I
calculation
figured out
stuff.
how the enantiomeric excess works.
Uh-huh.
Yeah, I can also pull something up on my iPad if it's needed.
Yeah, thank you. Thank you.
Okay, I have my thing ready. Just let me
Hmm.
know, or if anyone has, oh wait, I have a problem, like two problems I can do.
Hmm.
So, okay.
Yeah, let's do that.
All right. Do I have screen sharing perms now?
Yeah,
Okay, perfect.
yeah.
Okay, let me pull up this problem then.
Hmm.
Wasn't it- Wait, actually, it was on here. Yeah, okay. So the problem is S-naproxen, which has an alpha value of 66 degrees, is an analgesic, while its enantiomer is toxic. Say that you are given a solution that contains 1 gram of naproxen and 20 mLs of liquid, but the optical purity is not specified. You place it in a polarimeter tube at 10 centimeters and get a reading of 3.3 degrees from the polarimeter. What is the percent optical purity of the sample? Okay, let me make this. Okay. All right, cool. So I'm gonna get rid of that. That way,
Hmm.
people. Okay, perfect. So let's start off with just like R and S. So like remember R and S, these are optically active. So when you put it in a polarimeter tube, it's going to give some reading. So if you have like what you call it, plain polarized light, it's going to be, let's say, at 0 degrees. We're going to zoom that this is 0 degrees, and you can either rotate it clockwise or counterclockwise. So this is an example of what I'll say positive theta. This is an example of what some enantiomers could do. They can go the other way. So it can go positive, it can go negative. But we don't need to know exactly if R can go positive or R can go negative because that's completely unrelated. Okay. Um, so let's talk about specific rotation. This rotation value is called alpha. And alpha is going to be the number of degrees it rotates. And this alpha value is going to be taken at 589 nanometers. And it's defined for standard conditions as 1 gram in 1 ml at 1 decimeter. So if I had a tube which was shooting out the light, and then I had a sample that was about yay, and then, whoops, this length over here would be 10 decimeters. And then this would have a concentration of 1 gram per milliliter. And this is just going to be the thing that's going to be shooting at the light. So it's really important that you get this ratio correct because a lot of times what they're going to do in the practice problems is they're going to give you a variety or they're going to give you something about this ratio that's going to make everything super, super, super confusing. But don't worry about it because here's what we're going to do. So there's another equation that you need to know. The reason that we use this optical value is because one of the things that chemists want to do is they want to see if you have a mixture of something, what is the optical activity of that mixture? Because depending on what you get in that mixture, that's the observed value, that can tell you whether or not you have some impurities in your sample. What we can do is we can say that the alpha of the mix divided by the alpha of the pure sample gets you something called the enantiomeric excess. So let's say, for instance, just as a background, let's say I had I don't know, what's a good molecule? Caffeic acid. And then let me just move this around. Okay, so let's say you had caffeic acid, and let's say this it could have some stereochemistry or whatever, or let's just make it like that. Let's say you had this molecule over here, and then it could have a chiral form. Now, let's say for instance, this is the chiral center right over here. Now, if there's two different isomers of that, they're going to be enantiomers to one another. So that means that they're going to have an R and then there's going to be an S, and they're going to have opposite values. So let's say, for instance, the pure form, this is a complete hypothetical. This is not going to be real whatsoever. Let's say the R's alpha is equal to plus 22 degrees. So that means that the S alpha is going to equal to negative 22 degrees. And these are pure values, okay? Okay. Now, if these are the pure values, something that a chemist might do is, let's say they're making a molecule and this is one of the steps that they're trying to make. Like, let's say this is the molecule they're trying to make and they want to see, I want to report how pure my new method was. And in that, there's going to be a mix of some R's and then some S. And that's going to affect the alpha that you get. So I'm going to call this alpha effective. Or or oftentimes you're going to see this as alpha mix. For simplicity purposes, I'm going to say alpha mix. What people will say is that the alpha of mix, which is the observed rotation of your whole sample, is going to be, I'm sorry, yes, your alpha mix, which is going to be the observed sample, is going to be dependent on a few things. It's going to be dependent on the alpha of your sample divided by the length times the concentration. So, oh, I'm sorry. I'm so sorry. That alpha mix is over here. So let me just quickly backtrack just so that I don't confuse anyone. Sorry. So like I mentioned over here, when you make a compound, you're going to have a mixture of different isomers. So we want to observe the rotation of like the whole system. That's what we call alpha mix. In order to determine how much of each enantiomer we have, we use alpha mix and divide it by the alpha pure. Because for instance, let's say I had 50 of the R molecules and 25 of the S molecules. So that means that 25 of the R and 25 of the S, they're going to cancel each other out. So that means that I would have 25 molecules of R over 75 total molecules. So this fraction will allow me, this is kind of the logic of the fraction, the logic of the math behind this. This fraction will help me determine how much of one I have versus the other. So we can talk a little bit about that through this example. Um, let's say so this problem over here is not talking about that, but this is a good problem that ties in the last thing I'm going to mention. So alpha mix, let's say for instance, in this mixture or in a mixture of R and S isomers, I have an alpha mix of, which is equal to, let's say 10 degrees. And let's say that I wanted to do the alpha pure of, and this is positive. And let's say I wanted to figure out how much of my R versus S I have. Okay, what we can do is we can say this. Alpha mix over alpha pure times 100% is going to get me the optical purity, also known as enantiomeric excess. So it's, yes. So 10 divided by 22 times 100%, and let's see what that's equal to. 10 divided by 22 times 100. That's around 45%. So just to make the math easy, it's 45%. That tells me that I have so I will have some amount of S and I'll have some amount of R. but I'll have 45% more of R than I will have of the S. That's what this is saying. And these two over here, they're going to cancel each other out. That's why you will see some optical activity in this mixture. So if I wanted to figure out how much exactly I would have, I could do this calculation. I could say, hey, I know that if I have some amount of the S isomer, and then I had some amount of the R isomer, but then I also had 45% more of it, the total fraction, the total percentage sum has to be 100%. So 2x plus 45 is equal to 100. 2x is equal to 55. Make that a little neater. So x is equal to, I don't know, 20, what is 27.5%. So that means that I would have 27.5% of S and 72.5% of R. Okay. And this is just talking about how to calculate enantiomeric excess. There's another thing that we have to know about, especially when it comes to problems like these in optical activity. Earlier, I defined the standard condition to be 1 gram, 1 milliliter, and 1 decimeter. These values are important for a specific reason. And let me see if I can pull up a nice LaTeX version. Okay. Perfect. There we go. The formula that I just put on the screen is the formula that you will need to use for a lot of these problems. And let me explain what this says. This says that the specific rotation of a molecule is going to be in terms of a few constants. It's going to be in terms of the observed rotation. So for instance, if I had some amount of sample, the observed rotation, for instance, in this case, was 10 degrees. And then the concentration is in grams per ml, and the path length is the decimeters that we mentioned. You can think of specific rotation kind of like specific heat. Different objects and different materials are going to have different specific heats. Similarly, they're going to have different specific rotation. So this is going to be a constant for every single given chemical. The reason that this is really, really important is because of the following problem that we're actually going to go to above. So let's do this now. Let me pull this over to the side. That way it's just easier and it's cleaner for people to see. Let me get rid of that. Okay, cool. Any questions so far before we start? Cool, okay. Um, we'll start off by saying what we know. So we know that the specific rotation is positive 66 degrees. We also know that we have 1 gram per 20 ml, and this is just information that's given to us that I'm doing. And then it's at 10 centimeters. And then the observed rotation is equal to plus 3.3. Okay. And they want us to find the percent optical purity. So what we need to find is optical purity, also known as enantiomeric excess. Okay. So does anyone have like an idea of where we could start doing this problem? Or does anyone want to suggest something about how we can try doing this? No? Okay. Um, let's start off by using this equation that we had earlier. So we know that the specific rotation is 66 degrees. So let me copy this formula. Alpha D, which is the specific rotation for S naproxen, is equal to the observed rotation divided by the length times the concentration. Now, let's plug in some values. 66 degrees is equal to, alpha of the observed which is 3.3, divided by the length of 10 centimeters times 20 milliliters. I'm sorry, 1 gram per 20 milliliters. So 1 over 20. But I want to make sure I'm doing this correctly. So before we do this, we have to check the units. So the units in this case of alpha are going to be in degrees. So that's perfectly fine. And then we know that the observed rotation was this, but the specific rotation is this. So what we want to do is we want to figure out, if we want to figure out what the percent optical purity is, remember, this is just going to be alpha of a mix or a sample divided by the alpha of the pure times 100%. Okay? So because in this case, what we did here was we actually messed around with the standard conditions. We have to account for that in this measurement. So I'm going to show you what I mean. What I like to do in a problem like this is I like to figure out what the exact, or figure out what the manipulation factor was. Instead of having to plug in a bunch of different numbers and end up doing a lot of math, I'm just going to plug in the factor of change, which simplifies things greatly. So standard conditions for L is what, 10 centimeters. And in this problem, it's the same. So there's no change. But the concentration is usually 1 gram per milliliter. But here, it's 1 gram per 20 milliliters. What that means is we have a factor change of 20. So that means it's times 1 over 20. Okay. What I can then do is I could say this. Given that this value is, the alpha, and this is also another alpha, and if I know that these two values can't change, we can manipulate them because they are observed values and constant values. But we could change this value and we could change this value. And what you end up doing is you end up saying, okay, this value is only changing by a factor of 1, whereas concentration is changing by 1 over 20. Because of that, what you end up seeing is that when you do the math, this 3.3, which is up here, gets multiplied by 20. So let me say that one more time. So alpha over L times C is becomes alpha over a factor of 1 times a factor of 1 over 20, which is the same thing as 20 over alpha, 20 times alpha. And that's 20 times of 3.3, which is equal to 66%. I'm sorry, not percent, degrees. So that means that the actual sample, if we took it in standard conditions, would have 66 degrees of rotation in plane polarized light. That's important because this is the alpha of the mix, or also known as the alpha of the sample. So alpha of the sample, which is also AKA alpha mix, is going to be 66 degrees. So we can plug that back into our equation. We know that the pure sample has 66 degrees of rotation. And we know that the mix or the sample that we got had 66 degrees of rotation under standard conditions. So 66 divided by 66 gets us 1, and 1 times 100 is 100%. So that's why our answer, optical purity, is 100% in this problem. Any questions? Cool. Yeah, thanks, Brian.
Yeah, of course, Nern. That's good. That's good. Are you like in Verahad's class as well, like 118A, or like leave-ins, or did you check 118 with them, or?
I'm in 118 right now with Farhad.
Oh yeah, that's good. That's good. Are you in a research lab or something like that?
Oh yeah.
Oh yeah. That makes sense. Right, that's good. That's good. You asked me about 118C as well, about like the thing privately. I saw. I was like, dang, is someone is a tutor here? Like, are you tutoring for Gen Chem as well, or something?
Yeah, I'm tutoring for Gen Chem. I asked because
Yeah, ATC. Yeah.
Yeah, I saw a paper with that and I was like, oh,
Uh-huh.
that might be interesting. Maybe they do it for something else as well.
Oh, right, with the Benzyme intermediate right there.
Yeah.
Yeah,
Yep.
yeah. Let's see, it's good. Activation anion, pseudo SN2 pathway. Let's see. That's good. And the problem that you work on, was that from Farhad's practice exam, practice midterms or practice problems?
Yeah, it was from a set of practice problems that was on the Chem 118 Discord.
Oh, okay, okay. I see. That's good. That's good. Yeah, that's perfect timing too. Like it just hit 11. So thank you, Naren, and thank you everyone for coming. I'll post the recording probably tomorrow morning, and good luck on your exam on Monday. Hmm.
All right, thank you.
Yep, of course, of course.
Thank you.
Yeah.
Oh, where will the recording be posted? Sorry.
Yeah, it'll be on the Discord. I'll send it to the chat and
Okay, sounds good.
YouTube, my YouTube as well.
Okay,
Yeah,
perfect. Thank you.
of course. Yeah. I'll post the notes right now though. The ones I have.
Thanks, Brian.
Yep, of course, Ashna. Mhm.